Hi, my name is Kyle Gooding, and this is my final presentation for EE 478 under Professor Maduri, and my topic for tonight is going to be D algorithm for ATPG. My agenda covers all my paper topics, the introduction, requirements for the algorithm, meaningfulness of the algorithm, some examples, the automation process, a collection of D cubes. I'm going to explain what those are later, identifying conflicts with something called implication, alternatives, and expansions for the algorithm. Just a brief introduction, ATPG stands for Automatic Test Pattern Generation. It deals with testing circuits as they are built. So this is dealing with circuits coming out of a manufacturing process, and you're testing them to ensure build quality and to ensure that the circuit functions properly. It used to be done manually, no longer feasible just due to the growing size of circuits and growing quantity as well, making a manual test just far too cumbersome. This particular algorithm has been in place since 1966, where it was written by a gentleman named Roth, who happened to be working for IBM at the time. So requirements for the algorithm. It's written for combinational circuitry. It has to have binary logic as well. So in my examples on the right-hand side here, A, B, and C would all take on binary logic, as would the internal signals D and E. The only difference between these two circuits is a stuck at zero fault on D. Now the whole point of the test is to determine if there is in fact a stuck at zero fault. It's unknown until it goes through the process here. So the general procedure to determine if there's a fault starts with truth tables of all the logic gates. Then it moves to singular cover and then making D cubes. Now those first three steps are purely definitional. So once you've done them once for a logic gate, you don't have to repeat them again. You just can move right into any specific circuit that you're looking at. Step 4, propagate to the output, and then backtrack to the input for step 5. So again, we're going to start with just definitions before moving into an actual example of how this procedure would be used. So let's look at a standard OR gate. For a 2-input OR gate, on the left-hand side here, we see a truth table that I'm sure we've seen several times. For a combination of 0, 0, for the 2 inputs, you get an output of 0. For any other combination of inputs, 0, 1, 1, 0, and 1, 1, the output is going to be 1. For singular cover, again, that's one of the first definitions of this algorithm. What we're concerned with is that we actually maintain this 0, 0, 0, but then you move to something x1 gives you a 1, 1x gives a 1. X represents any value. Essentially, if B is given to be a 1, A can take on any value, which is represented by X, because the output is going to be 1 no matter what, based on what B was. Same for the last line. If A is given to be a 1, B can take on a value of X, because C is going to be a 1 no matter what, regardless of what B is. Then in order to describe what a D cube is, we first have to understand what a D intercept is. I have here a chart of all possible D intercepts. So there are 5 inputs to any logic gate in D algorithm: 0, 1, X, D, and the inverse of D. We've already seen the first 3. D is going to be a variable that is given to any fault that's going to be propagated through a circuit. That'll be explained later. D inverse of D is exactly as the name suggests. It's simply the inverse of the variable. So let's look at a D cube. Again, we're looking at an OR gate. On the left-hand side here, this is a graph that is borrowed from previous slides. This was 0, 0, x, 1, 1x to give the outputs 0, 1, and 1. Again, this is for an OR gate. If we were to combine the first line and the third line, they will yield the first line of our D cubes based on the intercepts of the previous slide. So for A, if we have an input of 0 and 1, I'm going to combine those using my D intercept page, 0 and 1, that's an output of D, which is given here. For B, 0 and X, 0 and X provides 0. It's given here. Likewise, if we were to do the same thing for C, we get an output or a D cube of D, 0, D. The other option is 0, D, D. So what does this D cube mean for us? It's a series, or rather a vector variables that we can use to propagate a signal through an OR gate without actually having to see the rest of the circuit. It allows us, for the first time, to generate these inputs procedurally to any logic gate that happens to be in a circuit. So it kind of takes the creative process out of testing. So it removes the necessity for a manual test. It allows a computer to do it. Again, this is the first algorithm of its kind. It came out in 1966. So I'm going to look at an example just to kind of walk through how this would look. So we're starting by assuming there's a stuck at 0 fault on node A. So that node receives a value of 1, but what we're actually going to assign it is the letter D. So that was step 1, just to assign D to the stuck at fault. Step 2, this D has to propagate towards the outputs. So in order to get a D here on H, it has to propagate through an XOR gate. And I've used a D-intercept to do that. I haven't shown you the actual D cube for that. That'll come at a later point in the presentation. But the D that we had here is going to propagate through the XOR gate to this point before 3. Then this NAND gate, again, we're going to allow it to propagate using a D cube that actually assigns a value to 1 on K. So steps 1 through 3, we're getting a D to H and then again to the output. From there, the algorithm goes backwards, starting with it knows there's a 1 here. In order to get that 1, we had to move through an OR gate. This value had to be 1 due to the NOT gate here, which means that the overall input D was a value of X, didn't matter due to this 1, which puts a 0 on F. If there's a 0 on F, C has to be 0 as well as E, which moves us back to 0.7 here. E was a 0, therefore B was a 0. And then again, we had a D before this 0.7. So the algorithm starts at a fault, moves to the end, and then backtracks all the way through the system. Another example, just to show that you can start with any fault line. We're starting here in the middle portion where my cursor is, that's currently unlabeled. It receives the value of D, propagates through an AND gate. D, D, this is a NAND gate, so you get inverse of D. So step 1, assign. Step 2, propagate. And then step 3, a consistency check, also known as backtracking. Move all the way back through the system to get your overall inputs. It's a relatively simple thing to talk about, but again, this was revolutionary in 1966 when it was first shown to be able to test these things automatically. So the automation process. On this slide, I really just wanted to highlight that a machine can perform these tests. So what it essentially allows us to do is it implements a search grid. So here on the right-hand side, I have a circuit on top. Again, the actual specific layout of the circuit is relatively arbitrary. But in part B, I've assigned a fault after this AND gate labeled S. And what we can show is that through this use of a general search grid is you can start with the point after S, assign it a value, move to the next point that's required, so in this case it would be L or M, assign those a value, move to R, assign that a value, K, assign that a value. You've automated a portion of testing that was typically and historically a more creative and less predictable action. So this is a general formula that can be used by other patterns. So what made D algorithm so special wasn't necessarily how it does things, but just the fact that it proved that it was possible. On this slide, and again, this is section 7 of my paper, is a collection of D cubes for select regular 2 input logic gates. So across the top here, unfortunately, they're not labeled, but this is the truth table for an AND gate. Immediately to the side of that is the single coverage for that same AND gate. So we've moved from 4 lines to 3, and then from 3 lines to 2 when you move to D cubes. And again, what this is going to let us do is allow us to approach any AND gate and D propagation is going to be one of these two options. So we've taken something that could be very complex by having 4 inputs and moved it down to just 2. The next line is a repeat of our OR gate situation that we've already seen. We saw the D cubes, D0D and 0DD. And then finally, this is for a NOT gate, or just a simple inverter buffer. 0, 1, 1, 0. If you have an input of D, you have an output of the inverse of D. It works all fine and well for all of these standard gates, but when it comes to an XOR gate, that's when the algorithm kind of struggles a bit. If we were to try to make a single coverage of the XOR gate, you can see on the output here that there is no 1. There's simply an X, and a 0, which makes it very difficult to try to convert this into a D cube. What I found in my research, which I explain in depth in my paper, is that what we have to do for an XOR gate is essentially treat it as if it were a faulty OR gate. For the sake of time, the D cube that works seemingly well for an XOR gate would be 1, 1 D inverse or 0, 0 D. So essentially what you're doing is you're taking each input, you're setting it to high, and if there is a stuck at fault, so example, we're testing for stuck at 0, so we try to push a 1 onto it. If it's a 1 input, the output is going to be D inverted. If it is actually stuck and there is a fault, that line is going to be a 0 instead of a 1, which is going to change the output of the XOR gate. So there is a complication when it comes to D cubes for XOR gates, which has been a motivation to try to come up with other algorithms based on the D algorithm that work with this a little bit stronger. That's the first conflict, is XOR gates, and the first kind of disadvantage of D algorithm. The next one comes with backtracking and proofreading. It is possible to have a circuit such as the one labeled here, where it's possible for the output of T to be something like a 1, which would require M to be a 1, but on the other side of this exact same circuit, M would also have to simultaneously be a 0 in order for testing to work properly. Circuits like this, where we have an M that fans into 2 gates and then reconverges back into a single gate, is called reconvergent fan-out, which causes other problems. Again, this comes to backtracking and proofreading. Something that the D algorithm tries to use in order to fight issues like this is called implication, which is essentially an automated feature that just says, is this possible? So in other words, when you go to propagate to the end and then backtrack back to the inputs, at every step along the path there, it checks, is it possible for both of these inputs to be happening simultaneously? And if the answer to that question is no, then unfortunately the test has to stop. But again, that's another motivation to come up with more algorithms that are based on this D algorithm to work on something like this, which is exactly what we've done here. So as the first algorithm that was actually inspired directly by the D algorithm is something called PODEM, P-O-D-E-M. It came to be right at the start of the 80s in IBM. The reason it came about was IBM switched to using DRAM, which uses a very high amount of XOR gates. And as we described before, the algorithm kind of struggles with the XOR gate. This alternative is centered around the primary inputs to the entire circuit, which we can kind of see here: assign a binary value to an unassigned primary input, and then determining the implications of all primary inputs. In essentially this alternate to D algorithm, which again is outlined very well in my paper, much more so than this 10-minute presentation, it really centers around those primary inputs as opposed to internal signals, which the algorithm really focuses on. And then after PODEM came something else called FAN, and this is an actual diagram from the 1995 paper that published FAN. It's an expansion on PODEM, fantastic for reconvergent fan-outs, because it uses something called incomplete backtracking. So when it goes to analyze a circuit such as the one here, if we have a complete path from, say, N to Z, it doesn't necessarily need to backtrack all the way to M, K, or L. It's content to stop at those points, and it allows testing to go on regardless of the input. It's worth noting that all three of those that I just said, the D algorithm and the two expansions that I listed, are all considered to be full algorithms. They all will find a valid test solution if there is one available. The difference between them, though, is just the speed at which it can find that algorithm. And that speed can be very critical when there's time and money on the line, and that's kind of the reason that people are looking for more algorithms. Moving back to a D-algorithm-centered view, though, for the final the final topic of the paper, we look at expansions of D-algorithms, and just kind of keeping in mind that it is very relevant today. Even though it came out in the 60s, it's still in use today. People are still innovating on the actual algorithm itself. For example, people have recently found it's possible to concurrently propagate forward and backtrack through the circuit, just to save time, to save effort. Granted, that is only possible right now on circuits that are reconfigurable or written on reconfigurable hardware, but it's still making progress. It's also very useful for circuits with odd gates or non-standard gates. And the reason being is if you can write a D cube for a particular gate, even if it weren't necessarily a standardized one, the algorithm can handle it through use of a library. So there's really interesting things that are going on for D algorithms even today, even though it's an older system. So just to conclude here, it's the original automated test pattern generator made by Roth in 1966. It kind of founded the D notation, which is used in plenty of other ATPG algorithms today. It's been expanded on multiple times, and it's still in use today. Thank you, and I really hope you enjoy reading my paper. I appreciate it.